Okay, so today we are going to speak about conditional expectation. Okay. And I need this notion typically because in few sessions we are going to speak about martingales. Okay, so we need this. Okay, it's the chapter 0.5. First of all, I have to check for attendance for the alpha in alternance. Okay. So Shakir, no. Lydia. Khadija. Dalia. Well. Myriam. Alice. Iman. Igal. Marion. Marine. Brian. Briand. Avec un A du coup. Nour. Non. Michel Matteo. Mélissa. Les autres je ne fais pas parce que obligatoire. Ok. En finance? Peu importe. Non, c'est que les finances. C'est obligatoire pour la finance. Il y a des cours qui sont obligatoires pour toi en assurance. Mais... Ok. And we are going to do so the construction of the conditional expectation, okay, step by step, in order to go to the general definition. Okay. So the first case is conditioning with respect to events. Okay. So I am in this situation. So as usual, I have a probability space, omega AP. Okay. And I consider a set in my sigma algebra. So just concerning the mask, okay, you put it on the mouse and put it on the nose, okay, both, for everybody, okay. I know that it's boring, okay, it's hot, but I do, so you will do, okay. So I have a probability space, so I consider a set in my sigma algebra, okay. And I would suppose so that PB is well defined because A is an element of the sigma algebra. I suppose it to be strictly positive. Okay? And you know from previous courses what is P of A given B. Do you remind this? What is P of A given B? The probability of the intersection over P of B. Okay? And that's why I impose P of B to be strictly positive, because I want to be able to divide by. Okay? And in fact, you know that from an intuitive point of view, this formula means that in the computation of the probability, you take into account the fact that you know B, that is, okay, you change the universe. You pass from the universe omega to another universe that is B. Okay, so this notion of conditional probability is related to a change in the definition of my universe. Okay? So this is the conditional probability of a set with respect to another one, another set. Okay? With the only constraint that is P of B is strictly positive. If I do this, I can define what we call the conditional probability given B, that is the following mapping. PB is something from my sigma algebra A into 0, 1 that associate to a set A, P of A given B. And we can prove basically that PB is a new probability on calligraphic A that is called the conditional probability given B. Okay? So it is possible to do this, okay, for any event, capital B, okay, in the sigma algebra calligraphic A with PB strictly positive. Okay. So it's very basic to prove that I have a new probability here. What is a new probability? Just something that fulfills PB of omega is equal to 1 and that fulfills the sigma additivity property. Okay, it's very basic to see that this one fulfills these two conditions. Okay? Okay. If I suppose a random variable x belonging to L1 of omega AP, in fact, it is possible to define the expectation of x given B. Okay? So a priori, the notion of expectation here is related to the probability, the initial probability I have on my space, okay? And this conditional probability given B, okay, is equal to what? Is in fact simply the expectation of x with respect to the new probability PD, okay? And we have a formula for this, that is, it's the expectation of x indicator function of B over P of B. So I have this one. So just a remark concerning this definition. In fact, so it's just a new expectation with respect to the new probability I call the conditional probability given B. And you can just remark that if I take in this formula for x the indicator function of A, you recover P of A given B equal to, if I have here the indicator function of A, I have the expectation of the product of the indicator function, that is the probability of the intersection, over P of A. Okay? So in the case of a single event, okay, the notion of conditional probability or conditional expectation is related to something you know perfectly, okay, from the previous courses. Okay? That is just the definition of the conditional probability. Okay. See, this is what happened for a single event. Okay? So I continue my definition. We have questions? For the moment? Yeah?
Quand vous mettez 1 indiqué, c'est P appartient à quoi?
Ça?
En bas. Sur l'espérance. L'indicatrice, mais c'est l'indicatrice de quoi?
De B.
De P.
L'ensemble de B qui est là. Indicator function of B. Indicator function of B, it's a mapping from omega into 0, 1 that associate to, let's say, x. 1 if x belongs to B, and 0 otherwise. Okay? The mapping, random variable if you want. Okay. I don't put the argument, I don't put the argument in capital X. Okay? This is the indicator function definition. Okay. So if I have it for sets or for events that are just set in my sigma algebra, okay, I have it easily with respect to discrete random variable. Conditioning with respect to discrete random variables. So what is the meaning of this one? So you know that a discrete random variable is a random variable taking values in a space that is countable. Okay, dénombrable, countable. So suppose that you are in this situation, so let capital Y be a discrete random variable and denote by capital D the set of the possible values. And since I know that Y is discrete random variable, the set of the possible values is countable, so maybe written as a sequence. Okay? So I write it this way. Y1, Y2, and so on. It can be finite or infinite, but at most, okay, as a sequence. And we suppose that in capital D, I have real values for Y, that is, okay, the probability that Y take a value in D is strictly positive. It means that I want real possible values for capital Y. If a value is such that the probability to take this value is 0, I remove it from the set capital D. Okay? So let Y be a discrete random variable taking values in D such that the probability of each value to really occur, okay, is strictly positive. And why I do this? Because as in the definition of the conditional probability here, I will need to divide at the moment, okay, so that's why I want them to be strictly positive. Okay. So by analogy with what I have done previously, okay, we are going to define in this case the conditional probability given Y and the conditional expectation given Y. So in this case, if you have a set in the sigma algebra, okay, what we define as P of A given Y, Y being my discrete random variable, is what? Is in fact the function of Y. So in this case, the conditional probability is not a number, it's a random variable. Okay, it's a random variable where phi of Y is equal to what? Simply the probability of A given Y is equal to small y. In fact, to define the conditional probability with respect to a discrete random variable, I just use the previous definition in the case of events. I have the right to do this because here I have an element of my sigma algebra with a probability that is strictly positive through my assumption. Okay? So just keep in mind that in this situation, okay, the conditional probability is not a constant, not a number, okay, but is a random variable that is a very particular random variable, the function of capital Y. Okay? The same for the definition of the conditional expectation. Okay? If I take x belonging to L1, okay, I can define the expectation of x given capital Y. It will be once again a random variable taking the form of a function of capital Y, where psi of small y is just equal to the conditional expectation of x given capital Y is equal to small y, this one being defined in the previous case. Okay? So you see that in the case of discrete random variable, since I take a countable number of possible values, the definition of the conditional probability or the definition of the conditional expectation, okay, is just an extension of what we have done in the previous section. We do the reasoning, if you want, events by events, taking for the events the set of the possible values for capital Y. Okay? So this is the definition of the conditional expectation in the discrete case. Suppose that I want to do an extension of this one for more general random variables. But in fact, if I want to do this, I have a problem here. Why I have a problem? Because for this formula, okay, I need this. And typically, suppose that you want to do the same for continuous random variable. It's not possible. Because by definition, a random variable is continuous if the probability to take one particular value is 0. Always. Okay? So what I have done here in the discrete case, it's not possible to do it in the same spirit for other type of random variable. Okay? So I repeat, for the discrete case, I just do what I have done for the case of events using these events that are with probability strictly positive. The problem is that with this approach, it's not possible to do the job if I replace my discrete random variable by a continuous one, because for a continuous random variable, all these probabilities are equal to 0. Okay, so it's not a good idea. So that's why I have to do other things. And we are going to define now what is the most general way to define a conditional expectation. That is a conditional expectation with respect to a sigma algebra. So I erase, so I keep this definition, let's say. And we are going to give the definition of conditional expectation in the case of sigma algebra. Okay. So, as we have film of the class, okay, it is possible to switch off the phone. So I have it. The same for me. I think that mine has ring just before. Okay, I have to switch off. Thank you for doing it because I have to do the same for mine. Sous l'enveloppe, on se... So conditioning with respect to sigma algebras, okay? That is in fact the real definition of conditional expectation, the more general one. So conditioning with respect to sigma. Okay. So we are going to see the definition, and after I will do some comment, okay, and in particular some intuitive interpretation of this definition. Okay. So I consider the following situation. So once again, I have my probability space omega AP. Okay, and I consider a random variable that is in L1. In particular, okay, this notation means that I am measurable with respect to the sigma algebra calligraphic A, meaning that any preimage of a Borelian by capital X belongs to calligraphic A. It's the meaning of being a random variable with respect to this probability space. In the case of the conditioning with respect to a sigma algebra, we are going to consider a new sigma algebra, another one, okay? So I just take the same notation in the one that I just noted. Is this one J? Okay. Let J be another sigma algebra such that I want it to be included in A. I want it to be included in it. Now, just a remark before to give you the definition of what is the conditional expectation of X given by sigma algebra. So you remind that I will use capital later for sets. I will use calligraphic letters for sigma algebras, okay? And lowercase later for evens in general, okay? So just a remark concerning these two sigma algebras. I can consider this L1 space, so the set of the random variable in L1, okay, with respect to this triple, and this one. Are you able to compare these spaces? I said that one is smaller. My question is which one?
The second one, right?
The second is?
It's smaller.
Okay. And my question now is why? Yeah, because I have this one, but keep in mind that the random variable is a mapping from omega into R. For the real numbers, okay, in general, we'll always take the Borel sigma algebra, the one that is generated by the open intervals, or the open sets, as you like. For omega, I may have several choices for sigma algebra, okay? Here, typically, I have calligraphic A, or I have calligraphic J. And I remind you that if I have the sigma algebra here, okay, I don't give it a name, but this one here, I know that X is a random variable or measurable, it means the same thing. If and only if, for all B belongings to B of R, X minus 1 of B belongs to point. This one, okay? So, of course, if I change the sigma algebra, I change my definition of being a random variable. And typically, if I am in this situation, of course, if my preimage belongs to J, my preimage belongs to calligraphic A. So it means that if I am measurable when I put as the sigma algebra here calligraphic J, okay, then I am a random variable also in the sense of calligraphic A, because I have this inclusion, okay? So that's why, in particular, this set is included in this one, because if I am a random variable with respect to this sigma algebra, I am a random variable with respect to this one, because if my preimage is here, it will be here. Okay? So it's important to have this definition in mind, in particular, because next session, okay, we are going to speak about the fact of being measurable or to be a random variable for a stochastic process. That is, instead of considering only mappings, okay, I will considering stochastic processes that are, okay, a family of random variables indexed by the time. Okay, so you have to be okay with this notion of measurability for the next session. Okay, so this set is included in this one. It means that if I am here, I am not necessarily here. But if I am here, I am in this room. Okay. So definition of the conditional expectation given calligraphic chain. So in fact, this definition is a theorem that we will prove at the end of the chapter 0. At the end of the chapter 0, okay, we have a little section concerning what we call the Radon-Nikodym theorem. Okay. Whatever this theorem is, okay, we will see this again at the end of the chapter 0. And in fact, we will prove that this definition is without ambiguity thanks to the theorem. Okay? But for the moment, just state it. Okay? So I suppose that I am in this situation. I have this triple, this probability space. I have an element in L1 of omega AP. And I say the following. There exists a random variable Z belonging to L1 of omega GP such that the expectation of x times u is equal to the expectation of z times u for all u, j measurable and bounded. And I said, moreover, that z is unique. And when I say unique, it's up to almost sure equality. But if I have two that fulfill this, the probability that the first one is equal to the second one is equal to 1. It's the meaning of equality between random variables when I have a probability. So Z is unique, okay, up to almost sure equality. And I repeat the meaning of this last sentence, okay? If I have Z1 and Z2 that fulfill this, it means that the probability that Z1 is equal to Z2 is equal to 1. Okay? Okay. So this is my definition of conditional expectation with the mask, the now. I have this. So a priori, what I have done in the case of events was that natural, because in fact conditional probability, when I do the conditioning with respect to an event, it just changed the universe, so it's something that I can understand basically. Okay. Here in this situation, it seems to be a little bit more complex to have an interpretation about this one. Not really, in fact. Now, in the case of L1, okay, there is an intuition that is not that clear, but if I consider a little subcase of this situation, okay, I can try to convince you that this definition is in fact not that theoretical. So it's a remark here. And after I will comment a little my definition, okay? So suppose that you don't start with someone in L1, but with someone in L2, okay? So So expectation of the square finite, expectation of the absolute value finite. I know that this one is included in this one. Okay? Yeah?
If what belongs to L2?
X. So it is not that different, but in fact there is a big difference between L1 and L2. Which one? So you know that all the LB spaces are Banach spaces that are vector spaces that are complete, okay? But for L2 I have more structure than this. What is L2? In L2. What I have in L2 as a structure, okay, that I don't have in L1.
I know that the second order moment in L2 means that the second order moment is finite.
Yeah. It's not what I have in mind here, it's the definition, and I said that passing from this space to this one is not that neutral because in this one I have something that is very interesting for us here. L2 is what? From a functional analysis point of view. Person? Is that the way?
I think we can define a dot product.
Yeah, so it's an Hilbert space. Hilbert space. Okay, you have a scalar product here. Okay, so this is important to have this in mind, and it's really important in probability theory. So L2 of omega AP is an Hilbert space. And
What is in the space?
it's a Banach space that is a vector space that is complete. Okay? So be careful because I have lectures not at the beginning of the chapter 0, but as you have seen, I have started not at the very beginning of the chapter 0. The things are explained. Okay, and I have said to you during the previous session to have a look on the beginning. But I will remind, no problem. Banach space just means you have a vector space that is complete. Complete in the sense that every Cauchy sequence is convergent. Okay? And what is more is that here I have a scalar product. I have a scalar product, and what is interesting with this fact that I have a scalar product is that you have notion of orthogonality and so on. Okay? So you can do geometry in fact. You have the analogous of Pythagoras theorem or something like this because you have orthogonality. So an Hilbert space, what is the scalar product in this space? Okay, if I take two random variables in L2, x1 and x2, the scalar product in L2 is what? The expectation of the product. Okay? So the scalar product is equal to the expectation of the product. Okay, so I have an Hilbert space, okay, with a scalar product, so with the notion of orthogonality, okay? And what is interesting is that when I have a scalar product, I repeat, you can do geometry as you do in R square, for example, okay? Okay, so let's continue. So here, let's do a picture. I have here, it's a bad picture, but it's to have an idea. You have here L2 of omega AP. Remind that L1 of omega AP contains L1 of omega GP. If I put L2 here, I have exactly the same inclusion. Okay? So you have here L2 of omega AP, and I consider here L2 of omega GP. A here, G here, and I know that the second one is included in the first. Okay? And I have my X that is here. my random variable x. Okay, so what can I do if I am in a Hilbert space? If I am in a Hilbert space, I have notion of orthogonality, and so I can do orthogonal projection. It is possible for me to do the orthogonal projection of capital X on this subspace. In fact, it is possible to do orthogonal projection on any, okay, closed and convex set. This one is closed and convex as, okay, itself inverse. So why I do this? If I do this, okay, I do my orthogonal projection and I define a new point here that is pi of x. That is the projection of capital X on the set of the square integrable random variable with respect to omega g. I said, okay, what is the link with this one? The link with this one is this remark. What is the meaning of the orthogonality here? It means that this vector here, this vector, this one, is orthogonal to all the elements in the red space. Okay? So we have, for all u belongings to L2 of omega jp, we have what? So if I have u inside here, but I have the fact that u and the vector x minus pi of x then 2 is equal to 0 because I have the orthogonality. And what is the meaning of this one? Keeping in mind that my scalar product is just the expectation here, this orthogonality condition is just expectation of u of x is equal to expectation of u I of x. And in this situation, in fact, the conditional expectation, that is the random variable j measurable fulfilling this one, is none other than the orthogonal projection of x on the space L2 of omega g. And now it's interesting in order to have an intuition about this one. Intuitively, it means that what we call the conditional expectation of, and there exists random variable fulfilling this, okay, and it is this one that I will call the conditional expectation of x given j. And this conditional expectation may be seen in some sense as I have x that is here. It's the best approximation of x by random variables that are j measurable. If you are a measurable, you are not necessarily j measurable. The conditional expectation is, in some intuitive sense, the random variable that approximate the best, okay, capital X. Okay. The random variable that is j measurable that approximate the best, capital X. Okay. If I am in L1, I don't have these tools, okay, I can speak about orthogonal projection and so on, okay, but if I am in L2, okay, I have something that is really geometrical in order to have, okay, the notion of conditional expectation as an orthogonal projection and so as a best approximation of. Okay? So I just erased my remark, okay, it was just to explain to you that it is not that theoretical. There is an intuitive meaning below this definition. Okay? But I have the real interpretation in the case of Hilbert space. If I am in this space, I am not Hilbert, okay, I have only a Banach space. I can't do this, but intuitively it is the same meaning. conclude this definition, of course, Z is denoted as the expectation of X given J. Expectation of X given J. If I continue, okay, what is the conditional expectation of X given J? It's the unique random variable J measurable such that this equality is fulfilled for any U J measurable and bounded. Okay? And the fact that I take U bounded in the definition here is just because X and Z are in L1. If I want that the product is in L1 also, I take U to be bounded, okay, to be sure that I have no problem with the definition of the expectation. So this is the definition of the conditional expectation. Okay. So if I have it, in fact, now I will be able to have it for any type of random variable. So keep in mind that what I have done before this definition is to do the job for events, to do the job for discrete random variable. Okay. Remark that it was not possible to extend to continuous one because the probability to take a particular value is always equal to 0. I have introduced this definition, and now we are going to make the link with what happened for random variable. Okay. So 0.44 conditioning with respect to general random variables. Okay. So before we remark once again, okay. So if you have a random variable capital X, I repeat what I have already done, okay. I said that X is defined from the universe into R. I equip R with the Borel sigma algebra without ambiguity, but I said that on omega I can have several possible choices for sigma algebras, okay? And the idea is to say okay, that the notion of being a random variable will depend on the fact that okay, I have one sigma algebra here or another. If I change the sigma algebra, I change the definition of random variable. So I repeat something that I have already said, but I will write calligraphic F here. That X is measurable in this case, if and only if, for all B belonging to B of R, then what? Then X minus 1 of B belongs to delta. This notion being dependent on the choice of calligraphy. Okay, I repeat something I have previously said, but in order to introduce the following. If I have two sigma algebras, F1 and F2, two sigma algebras with F1 included in F2, okay, I said that X random variable for 1 implies X random variable for F2. I repeat once again something that I have already said, because if the pre-image is in F1, of course it is in F2. Okay? So if I am a random variable for F1, I am a random variable for F2. So if f1 is smaller than f2, the definition of being a random variable, okay, is okay simpler for f1 than for f2. In fact, I say that, and something that is in the beginning of the lecture's note, and something that you have probably seen before, that I can equip omega with a sigma algebra here that is minimal in the sense of inclusion in order to make x a random variable. In order to make x a random variable. The smallest possible in order to make x a random variable. So that is to choose f, okay, the small I can in order to fulfill this definition. Okay, it's what we call the sigma algebra generated by x. So it's a definition in the beginning of the lecture's note, okay, so I hope that you have read them. So we define by sigma of x the smallest in the sense of inclusion sigma algebra making x measurable. The smallest sigma algebra making x measurable. What is the sigma algebra? It's possible to define it in a good way. Now, if you have a random variable, it means that here you have chosen a sigma algebra, and you are sure that inside you have all the pre-image of Borelian by capital X. Okay, you have, by definition, all the x minus 1 of B have to be in calligraphy. Okay. What can I take for this one? In fact, we are going to take all the one I want, all the pre-image of Borelian, and in fact it is very easy to prove two things. First, that I have a sigma algebra here by the properties of the pre-image, and secondly, that this one is the smallest possible. So the smallest possible is very easy because I need to have the pre-image inside. I can't have less in the pre-image. If I prove that this is a sigma algebra, it's okay. It's very easy to prove because you know that the pre-image of the union is equal to the union of the pre-images, the pre-image of the intersection is equal to the intersection of the pre-image, and so on. Pre-image and operations on set, okay, have a very good behavior. So I have this. So, why I have introduced this? In order to remind you that if I consider x as a mapping from omega into R, it is always possible to equip omega with a sigma algebra that we call sigma of x, and that is the smallest sigma algebra that make x measurable. Okay? So I erase this for a moment. What is also interesting is that if you consider, let's say, t from omega into R, so I equip R with the Borel sigma algebra, and I equip omega, okay, with this sigma algebra, sigma of x. I have a powerful result that is presented in the beginning of the lecture's notes that tell me that t is measurable, that is t is a random variable. In this situation, if and only if, in fact, T has a very, very particular form. It means that if I put as a sigma algebra here, sigma of x, okay, T is measurable in this situation if and only if T is not that general, just T is a function of capital X. It means that if I am measurable with respect to this sigma algebra, I am necessarily a function of X. A result that is that stronger, in fact. So depending on the sigma algebra I put here, I have different definition of measurability. I have reminded to you the one that is minimal in order to make a random variable, and to make a mapping a random variable, sigma of x. And I have this result that tells me that if I am sigma of x measurable, in fact I am a function of x. Okay? And now I have everything to give what is conditioning with respect to random variable. Okay. It's a very short definition now because I have everything. So definition 0.4.2. Okay. When x belongs to L1 of omega EP. Okay. I define the conditional expectation of x given another random variable y without any kind of hypothesis on capital Y as the conditional expectation of x given sigma of y. So you have in the previous definition the definition of what is the conditional expectation with respect to a sigma algebra. If you have a random variable here, the definition of the conditional expectation of x given y is just using the previous definition, the conditional expectation of x given the smallest sigma algebra that make y measurable. The definition in this case is just a consequence of the previous definition. Conditioning with respect, in fact, to a general random variable is just a subcase of conditioning with respect to the sigma algebra. I just take as the sigma algebra sigma of y. Okay? So I have this one. So a remark and a consequence of this is that here, by definition 0.4.1, you know that the conditional expectation given the sigma algebra is the unique random variable that is sigma of y measurable and that fulfills the expectation condition. And in particular, this one being sigma of y measurable. And because of this result, we know that the conditional expectation given sigma of y is in fact just a function of y. Is of the form, in the same notation I have used, psi of y. Because this one is sigma of y measurable. If I am sigma of y measurable, it means that I am a function of y. So the conditional expectation given y is a function of y. If you come back to what I have done in the section 0.4.2, that is in the case where I deal with the discrete random variable y, I have defined the conditional expectation of y as a function of y. Doing the reasoning, okay, events by events. Okay, so this is the definition of the conditional expectation with respect to a very general random variable that is just a consequence of what happened in the case of sigma algebra. Of course, you have already computed conditional expectation, in particular in this case, even if you don't have seen the definition 0.4.1. In general, in practice, when you want to compute conditional expectation, okay, you use the notion of conditional density function. Okay? So in the following, you are just going to see the link between this definition and what you used to do, okay, in the case where you have a pair of random variables having a joint density, when you are able to define the density for the conditional density, okay, and just to compute the conditional expectation as integrals with respect to the conditional density. Of course, it gives rise to the same thing, okay, and it's what we are going to see now. Do you have questions concerning what I have done? So a priori, it's something that you have already seen, the definition of a conditional expectation with respect to a sigma algebra. Here, okay, when it is not the case, it was just a way to remind you the things, the basic things, okay? We are going to handle a little this definition just now, okay? So if you are able to do the conditioning with respect to a sigma algebra, you have everything in fact, okay? Because for random variables, it's just to do the conditioning with respect to the smallest sigma algebra that make y measurable. So if you are okay, I will erase everything. Okay, I will just keep the definition of the conditional expectation in this case here, and then we are going to handle it a little. Okay, no questions?
To show that T is measurable economically, T for the
It's the math.
enfin, to show the form, the expression of T when it is sigma x measurable. I don't remember what's the argument of it.
Oh, it's a real proof, this one, huh?
Sorry?
It's a really complicated proof in order to prove this. Okay, it's not that easy to prove. Huh? It's the equivalence. Okay, so of course this side is obvious. Okay, this side is more complicated. Okay, and if I remind the argument to do this, to be le nom en anglais, en français ça veut dire, c'est le théorème avec les petits systèmes, les petits systèmes, vous vous souvenez de ce genre de choses improbables? C'est ça. Oubliez. Peu importe. Monotone class theorem. Okay, that is the argument in order to do. Okay? Yes. We prove it by monotone class argument. So forget this, it was just to answer a question. This is the underlying argument, okay, that is, let's say, far from this course. Just keep in mind that if you are measurable with respect to sigma of x, you are a function of x. Okay? No more question I may erase? Yeah? By erase in the corner, I will put the definition of the conditional expectation and make the link with what we know or what we used to do in practice with conditional density. Question? No? It's the unique random variable. So, the unique random variable, I have said that is sigma of y in fact measurable, but the unique random variable of the form psi of y such that, because it is sigma of y measurable, such that the the conditional expectation of x u is equal to the expectation of the conditional expectation of x y u for all u of the form, let's say, h of y with h bounded. What I have done here, I have just copied the definition of the conditional expectation of x given sigma of y, keeping in mind that if I am sigma of y measurable, I am just a function of y. So here I have just copied the definition 0.4.1, okay, and just adapted to the fact that here the underlying sigma algebra is sigma of y, and so that I am a function of y, and u, that is sigma of y measurable and bounded, is just a function of y with h bounded. Okay? So here, what I have written here, is the definition 0.4.1 in the case where for j I take sigma of y. Okay? Why I do this? Because I just want to make the link with what you know, that is the conditional distribution and the way to compute conditional expectation in the case where you have conditional distribution. Okay. So I suppose that I have once again x and y in L1 here, okay? I suppose that I have x and y in L1. And the hypothesis here, that I don't have done in the previous case, hypothesis, the pair xy has a joint density function. Joint density function that I denote by f of x. Okay? So it's a strong hypothesis that is not true in general, but here I suppose that the pair of random variable, hypothesis here, xy has a joint density function. Okay? So first of all, what can you say about x and y if the pair xy has a joint density function? What can you say about x and y? If the pair has a joint density function, what you can deduce for x and y?
They are measurable. They are measurable as like single.
They are measurable because by definition, what is the meaning of being measurable for a vector of random variable is just each component is measurable. Okay? But I have density here. Joint density. I have a pair of random variable. I know that they have a joint density. What can you say about the components? Okay, so in fact, they have a density function also. So if I have a joint density for the vector, each component has a density function. Okay? So in this case, x has a density, y also has density, and you are able to recover the density of x and y from the joint density. I've done this with me use here. Okay? Fx of small x is just the partial integral of the joint density with respect to y. Okay? And the density of y is just the partial integral of the joint density with respect to x. Okay? Okay? thing for you is that when you have the joint density and when you have the density of each component, it is easy to check if x and y are independent or not. So when x and y are independent,
When the joint can be greater than the multiplication of the two.
so two random variables in this situation when they have a joint density are independent if the joint density is equal to the product of the density of each component. Okay, so in order to check independence in this case, you just have to check if the joint density may be written as the product of the density of each component, and in particular, if you can separate the variable in the expression of the joint density. In general, they are not independent. Okay? So in general, they are not independent, but in the case where they are not independent, often, okay, we want to extend this kind of relation. In some sense, okay, to decompose the joint density using this. Okay? It's exactly what we do. So suppose that they are not necessarily independent here, but that you want to write something like this. Okay? What can I put here in order to have this one? So of course, when they are independent, it's f of x, but when they are not, okay, the one we can take is this one. Okay, but the only problem I may have is that when the density of y is 0. Okay? So, I repeat, I want to decompose the joint density this way. I say that here, what can I take? I can take the ratio of this one divided by this one. It is possible, but when what I have below is not 0, just in order to be able to do that. So, it imposes the definition of the joint density, as you have seen it previously. What we call the conditional density of x given capital Y is equal to small y at the point x is equal to what? Is equal typically to f of x y over fy of y if f of y is different from 0. And 0 otherwise. And we can prove that if you have this, okay, if you have this, you always have the following, that is the joint density can also be written as the product of the conditional density of x given capital Y equal to small y multiplied by the density of I have this. So if you want, the conditional density is what replaces density of x when we don't have the independence hypothesis. Okay, so this is the definition of the conditional density. Okay, and the way it is used in order to decompose the joint density of x. So it was just a reminder to remind you how the conditional density is defined. Okay, and I said that in general, okay, when in what you have done before, in order to compute conditional expectation in this case, it was just to compute expectation with respect to the conditional density, and my aim here is just to show you that this definition and what you used to do are of course the same. Okay? So this one seems to be a little bit theoretical, but in fact it's just related in the case where the pair has a joint density to what you used to do in practice. Okay? So you have the definition of conditional density here. Okay? And I write just the following statement here. It's more a remark than a property, okay? So may I erase this one, okay? That was just a reminder concerning conditional density. I keep the definition here of the conditional expectation. I erase this. And I say the following, okay? So, if phi of x belongs to L1, the conditional expectation of phi of x given y is equal to what? To a function of y. Where in fact, it's very easy to compute psi, or very easy in the sense that it is not more complicated than to compute an integral. That is, here, compute a conditional expectation is not more complicated than to compute an expectation. That is here, the integral, okay, minus infinity plus infinity of phi of x, conditional density function of x given y equal to small y, dx. Okay, I have this one. Okay, so I repeat that in the case where x and y have a joint density function, that is the purpose of this section here. If I want to compute the conditional expectation of a function of x given y, in this sense, I just have to compute, in fact, the integral with respect to the density, the conditional density function, as you used to do before. Okay? Here, the definition is just an extension of what you used to do in the case where I don't have a joint density. I don't have a joint density, I have a general definition, but if I have my joint density function, okay, I recover what you have done in the previous steps. I'll just have a look on this result, okay? The proof of this one. Proof of this one. I want to do a preliminary remark before to do the proof, and that is very basic, and that is just a consequence of this one here. I don't know if I do it now or a little bit later. I will do it later. Okay, so I want to prove that the conditional expectation defined this way is given by this expression. Okay? So, first here, I know that my candidate here is a function of y. Exactly what I want to have. I just have to specify that this function of y is given by what I have written here. To do this, okay, we are going to take this condition, that is a condition in the definition of the conditional expectation, and check that for this one it works. Okay? So let's start with the expectation of x times u, where I take for u the function of y, h. Okay, that is this one. Okay. So what is this? So this one may be expressed, okay, by using the joint density of x and y. It's an expectation of a function of capital X and capital Y. Okay? So I can write it as a double integral of what? Of x, h of y, f xy, xy, dx. Okay. I have written x here, but keep in mind what I want to do here. The conditional expectation of phi of x. So instead of having x here, I have phi of x, phi x, phi. Okay? I have this one. So I have a double integral. So it's a remainder, a little remainder that I will do a little bit later, but when you have a double integral, and typically here, because u is bounded, phi is in L1, so the product is in L1, I can use the Fubini theorem. In the sense that at this stage I can compute the integral in the order I want. Okay, I can compute the integral in the order I want, and I can write it this way. In fact, write it the following way. First, I do the computation with respect to x, and then with respect to y. But what can I do here? So again, I just compute first the integral with respect to x and then the integral with respect to y. It's the Fubini theorem. Okay, I will do in a few minutes a complete remainder concerning Fubini theorem. Okay. So I have this one here. And what I want to obtain, keep in mind what I want to obtain. So I start from the expectation of phi of x times u. I want here something where inside I have what? Here a function of y and u that is a function of y. So I want to express everything, okay, as an integral with respect to the density function of y. So I can here multiply by the density function of y here and divide by this. And if I do this, what I obtain here exactly as I have defined as psi of y. So it's an integral of h of y times psi of y multiplied by the density function of y dy, and it's something that I can express as an expectation that is just the expectation of h of y psi of y. At the end, what I have proved what I have proved, okay, I have proved that starting from this one is always equal to this one with this random variable that is a function of y, if I come back to this definition here, you see that the consequence of this one is that the conditional expectation of phi of x given y is just equal to psi of y. Simple. In other words, it's exactly what I have written here. That is, if you have a joint density for the vector xy, the computation of the conditional expectation coming from the theoretical definition is not more complicated because it's exactly the same as what we used to do previously, that is, using the conditional density function. Okay? But unfortunately, in general, we don't have such conditional density function, okay, conditional density function. So this definition, okay, allow us to do the same kind of thing, okay, in the case where I don't have the joint density function. Okay? Okay. Allez, little break now. Ouais. Oui. I don't here when I write this one, it's Riemann. Mesure de Riemann. Okay. So yes, you can, but here, okay, I deal with density function here with respect to Lebesgue measure. So it's classical Riemann integral here. I will make some points on this just after, okay. In 20 minutes, I will remind the Fubini theorem, okay, with probability, expectation as integral with respect to probability. I will come back on this point. But here, it's just classical integrals. Okay? To be clear,
I had another doubt. For the proof, can we do the take expectation with respect to y, then taking it again, so it doesn't change anything? And then since h is a function of y, take it out, and then we'd be left with the second line there, and that would also bring down the solution?
here,
No, in the other one.
in this one here,
Yeah.
you have an expectation, but with respect to, yes. Okay, so we are going to see the properties of the conditional expectation, and before I remind it, the definition, okay, to have it in mind. So, x in L1 of omega nt, okay, J sigma algebra included in A, and we say that the conditional expectation of x given J is the unique random variable z j measurable such that the expectation of xu is equal to the expectation of zu for all u j measurable and bounded. Okay. Okay. So concerning the properties of the conditional expectation. So remind that in the previous session I have said to you to, if it's possible, to print the lecture notes or to have them on the phone, to have them on an iPad, okay, okay, it's better to print because you can take notes, okay, but you don't have a printer because it's not possible for me due to COVID restriction to give you the documents, okay. The process is really complicated. So, typically, okay, for one of the propositions we are going to see now, okay, I won't copy everything because it's that long, okay, and it's classical properties. Just what you have to keep in mind concerning the properties of the conditional expectation is two things. First, a conditional expectation is an expectation. So all the properties you know about expectation are okay for the conditional expectation. So I can write this way, and for the detail of the proposition, okay, see the lecture notes. It's the proposition 0.4.1 that I will write this way without giving all the details, but all the properties of the expectation are okay for the conditional expectation. So what I mean by classical properties of the expectation, okay, but it's all what you have. Positivity, linearity, monotony, the Bepo-Levy theorem, okay, you have the Fatou lemma, the dominated convergence, the Jensen inequality, okay, so all the things that are okay for expectations are okay for conditional expectation, okay? So you can use them. For the details of all of them, okay, it's just a reminder concerning the properties of expectation. Write them in the case of conditional expectation, but I won't spend time to write, okay, what is linearity, what is dominated convergence in this case, because it's exactly as in the case of expectation. Okay? So we can use all these tricks, okay, in the case of conditional expectation. What is more interesting for us today, okay, is the properties that are coming from this definition, typical to the conditional expectation. Okay? So I can write them this way, it's specific properties. So specific properties that are not true in the case of explanation, or even not, that are meaningless in the case of the expectation, and okay in the case of conditional expectation. It's the proposition 0.4.2. Okay. First, that the expectation of the conditional expectation is equal to what? Expectation of conditional expectation is equal to the expectation of x. The conditional expectation and the random variable itself have the same expectation. My question is why? Here I state, here I prove. Why? I come back to the definition, I have this here. Okay? In particular, I have this relation that is true for any u, j measurable and bounded. Here x is my variable and z is the conditional expectation. How to make appear the expectation of x and the expectation of z? Taking this is true for any u. If I want to have this, what I have to take for u here, that is j measurable and bounded. Oh, it's an indicator function, but a special one. Take one. One. Indicator function of omega. Okay. It's okay taking u equal to 1 in the definition here. If you take u equal to 1, you have here the expectation of x and here the expectation of z, where z is the conditional expectation. So you have the expectation of x that is equal to the expectation of the conditional expectation. Okay? Are you okay with this first? Now, I say that if x is j measurable, the conditional expectation of x given j is equal to what? Hmm? It's in the case of independence, this one. So here, so if I come back to the intuitive interpretation of the conditional expectation, I have said that the conditional expectation of x given j is the best approximation of x by mapping that are j measurable. But if x itself is j measurable, what is its best approximation? Itself. This one. Okay? And what is the argument? So my intuitive argument is the one with the interpretation in terms of approximation, but if I come back to the definition, first I know that x is j measurable, as has to be the conditional expectation, and I know that I can write this one, that is the stupid one, but I write this, having in mind that this one is j measurable. And by definition of the conditional expectation, this implies that the conditional expectation of x given j is equal to x itself because x is j measurable. Okay? The conditional expectation of x given j is the unique random variable j measurable fulfilling this one. If x is itself j measurable, taking z equal to x works. By unicity, it is necessarily the conditional expectation. Okay? I have this. A small c. I said that if y is j measurable and bounded, the conditional expectation of y times x given j is equal to y conditional expectation of x given j. So this property is known as taking out what is known. So what is known in the sense that I can take out from the conditional expectation something that is j measurable. I can take out this one and put it here in front of because it is j measurable. Okay? So just a little remark. Here I suppose that y is j measurable and bounded. Why I suppose it to be bounded? Just for technical reason, because I want that this product is in L1. Conditional expectation is defined for L1 random variables. X is in L1. If I multiply by y that is bounded, I have something that is in L1 also. Okay? But typically, I can replace y bounded, okay, by just the fact that I want that this one is in L1. So for example, if x is in L2, I can take y in L2. If x is in LP, I can take y in LQ with 1 over p plus 1 over q is equal to 1, and so on. Okay? So in general, this kind of property that is remove something that is j measurable from the conditional expectation will be okay if we have, okay, good integrability conditions. It means that each term has a sense. This one is in L1, this product is in L1. It works for y bounded, but I can restrict a little this condition to have a statement that is a little bit more general. Okay? But let's write this. Okay? So I have this. Let's do the proof. Once again, it's a consequence of the definition. I am interested in the conditional expectation of the product y x. What is this? So I am interested in the expectation of y x, okay, time u, for u, j measurable and bounded. Okay? Because of the definition. If I am interested in the conditional expectation of a random variable, I have to take the expectation of this random variable multiplied by u, that is J measurable and bounded. Here, my random variable of interest is the product yx. Okay? But I can write this expectation this way. X, y, u. And why I do this? Because I know that u is J measurable and bounded, and I know also that y is J measurable and bounded. So the product here is J measurable and bounded. Since this product is J measurable and bounded, by the definition of the conditional expectation of x, this is equal to the expectation of what? The conditional expectation of x given j multiplied by y times d. The argument here is because the definition of the conditional expectation of x given j. And because here I have something that is J measurable and bounded. And I say that in fact it's finished. Why it's finished? Because what I have done here, I have written the expectation of this one times u as the expectation of this one times u, where this one is J measurable. By definition of the conditional expectation, it means that what I have here is the conditional expectation of this one given j. The conditional expectation of yx given j is equal to this term. So the proof of this proposition is interesting by itself because it allows you to handle the definition. Okay? So I repeat, I am interested in the conditional expectation of this term. That's why I consider this term for you J measurable and bounded. I just remark that I can write it this way, where here I have something that is J measurable and bounded. So I can use the definition of the conditional expectation of x given j. That is the unique random variable such that the expectation of x given something that is J measurable and bounded is equal to the expectation of the conditional expectation times the product yu. And at the end, I have this equality showing that I have written the expectation of yx times u as the expectation of this one times u, where this expression is J measurable. By definition of the conditional expectation of this term is this one. Okay? Just definition of this. Okay. So if it's not clear for you, okay, it means that you have to work a little this definition. And I repeat, I do the proof of this proposition because I think that it's a good training in order to handle this definition. Okay. So it's more C. So if you're okay for the moment, so finish to copy, okay, and after I will erase because I need place to do the small d and the small e, because I want to keep the definition on the board for the moment. Okay? So maybe for small d I can write it here. That is the following. If x is independent of j, then what? Then the conditional expectation of x given j is equal to the expectation of x. So the link between independence and conditional expectation. So just a remark concerning my notations here. Here you have a random variable. Here you have a sigma algebra. The natural question is, what is the meaning of this one? But I have already said that for x, I have a natural associated sigma algebra, that is sigma of x. This one means that sigma of x and j are independent. And the independence between sigma algebra is just that for any element in the first and any element in the second one, the probability of the intersection is equal to the product of the probabilities. Okay, so I repeat. Independence of set, you know, probability of intersection is equal to the product of the probability. I can extend this definition to sigma algebra. It has to be true for any element in the sigma algebras. Okay? And for random variables or random variable n sigma algebra, the meaning of this one is just sigma of x and j are independent as sigma algebra. And also, for example, if you have two random variables x and y, to say that they are independent just means that sigma of x and sigma of y are independent. So this one just means that x and j are independent, and in other words, okay, concretely, it will mean that x as a random variable and any random variable that is j measurable will be independent. Okay, so once again, it's something that is reminding me the beginning of chapters here. Okay. So if x is independent of the sigma algebra, the conditional expectation is simply the expectation. Okay? A very particular case where my conditional expectation is no more a random variable but a constant equal to the expectation. So let's do the proof quickly, okay? Once again, I come back to the definition. What is the definition? So if I am interested in this term, okay, I consider the expectation of x times u, okay, for u, j measurable and bounded. So u is j measurable. I have said that to say that x and j are independent means that x is independent of any random variable j measurable. It means that x and u are independent. The expectation of the product is so the product of the expectations. But expectation of x is a number, so by linearity I can write this. By linearity I have this. That gives me the result. Why? Because I have expressed the expectation of x times u as the expectation of someone times u with this someone that is j measurable, and of course that it is j measurable because I have a constant here. It is j. Okay, so the conditional expectation of x in j is simply equal to the expectation. Small d and it's not small a. So you have the small d here. I erase the small a, small b, and small c. I keep small d on the board. And the last one is what we call the tower property of conditional expectation. Are you okay with the small d? Okay, independence and conditional expectation. Just keep in mind that the conditional expectation is equal to the expectation in the case of independence. Okay? And I repeat that if you are not totally okay with this little reasoning, spend time to study this definition at home. Okay? So I have this. Last property we are going to see. So I start with, okay, I have a priori. So when I have defined the conditional expectation, okay, I had my initial sigma algebra calligraphic A and my sub-sigma algebra J here. We are going to consider another sigma algebra, okay? Let J prime a sigma algebra such that I have J prime that is included in J that is included in A. Okay? I have this one. And then I have the following property. Then the conditional expectation of x given J prime is equal to the conditional expectation of x given. Okay. Intuition about this one and then the proof. So keep in mind that here, if I am G prime measurable, I am J measurable, and I am A measurable. Okay? So B G prime measurable is the thing that is the more restrictive here. Okay? L1 of G prime is included in L1 of J, that is included in L1 of A. What is the meaning of this one if I use the interpretation in terms of best approximation? So I have the set of all random variables, the set of the J1 and the set of the G prime 1. Okay? So it means that if I want to approximate X by something that is J prime measurable, I can do it in two steps. First, I approximate it by J measurable random variable, and then I approximate it using J prime measurable random variable. Maybe let's do a little picture. If I take the interpretation in terms of projection, you have here L2 of omega AP. You have here, let's say L2 of omega GP. And inside here, L2 of omega G prime P. The meaning of this relation is the following. So my picture will be very bad, but the interest is just the interpretation of what I will say. If I start with the X, that is L2 of AP measurable, what I have presented as the conditional expectation of X given G prime is the best approximation of X by G prime measurable random variable. I obtain it this way, considering the projection of X on this space. And another way to obtain this is to do this. Right? It will be bad, okay, but I can first do the projection on this set and then do the projection on the other one. It's exactly the meaning of this. First I do the projection on J, and then in the second step I do the projection on J prime. It's exactly the intuitive meaning of this one. Okay? With orthogonal projections here and here. Okay? If you have two subsets, one included in the other, if you directly project orthogonally on this one, it's the same as if you project here orthogonally and here. Okay?
And orthogonal in the, and the other one is orthogonal.
Yeah, here. But it's just, I have one color and only one, okay, so I do my best with this. Okay? So you have J prime here, J, A, X that is A measurable. The conditional expectation given J prime is obtained doing the projection on L2 of omega J prime P. And I say that it is equivalent to do first the projection on L2 omega GP and then to do the orthogonal projection on L2 of omega G prime P. That is the intuitive meaning of this. Let's do the proof without intuition, just using the definition. So once again, we are going to come back to the definition here. So I am interested in this one, and I want to prove that it is this one. Okay? So let's be interested in finding the conditional expectation of x given j prime. To do this, I consider the expectation of x times u with u that is j prime measurable. Okay? Because I want to use this definition with j prime instead of j. Okay? So, what I have? I know that u is j prime measurable. So it is in particular j measurable, because j prime is included in j. So u is j measurable. So, using the definition of the conditional expectation of x given j, I have, since u is j measurable and bounded, okay, I have this. I have this one. I repeat by the fact that u is j prime measurable and bounded, so j measurable. And I use the definition of the conditional expectation. Okay? Je sais, c'est simple. Je comprends. C'est pour ça que je ne fais pas justement. Pas simple. Then, u is j prime measurable, and here I have a random variable in L1. By definition of the conditional expectation given j prime, I can write here that this is equal to the expectation of what? Of the conditional expectation of this one given j prime times u. And it's finished. It's finished because what I have proved that if I multiply, if I have the expectation of x times u when u is j prime measurable and bounded, I can write it this way, where this one is j prime measurable. By definition, of the conditional expectation of x given j prime, this conditional expectation is necessarily this one. Okay, and it concludes the proof of this proposition. So it's really important to spend time at home on these proofs, okay, because we are going to use a lot in this course conditional expectation. Because keep in mind, if you have already done mathematical finance, that prices in classical models will be given by conditional expectations. So conditional expectations will be for us, okay, a key notion, even if we have mathematical finance in mind. So you have here the classical properties of the conditional expectation that are specific properties. They may be added to the classical properties of expectation that are linearity, positivity, Jensen inequality, dominated convergence, okay, monotonic convergence theorem. Okay? Questions? Well, for some of you, it's something that you have already seen during the second semester of the previous year, but I prefer to remind. Okay? No questions? So now we are going to see a little proposition that will be very, very important in this course. It's something that we are going to use a lot in this course, so I want you first to understand it, okay, and to be able to prove, because in the proof, okay, you have a lot of interesting things. Okay, it's that short, okay, it's just the particular way to compute conditional expectation in a very particular situation that will be the one we deal with, okay, in most of financial models. Okay. So if you are okay with definition, proposition, proof, I erase everything. If you don't have questions, I can erase. Let's erase. So I erase everything. Fini à 8h30. Half an hour. So I repeat, okay, this proposition, the one we are going to see now, okay, will be used a lot of time in this course. So first I will state, then I will comment, and then I will prove. Okay, so it's what? Proposition. Here, no, it's here. Proposition 0.4.2. Proposition 0.4.2. Okay, so important in this course. Okay. I suppose the following. I will consider, okay, x and y, two random variables such that what? I suppose that sigma of x is independent of sub-sigma algebra J. Sigma of x is independent of J, meaning that x and J are independent. And I suppose y to be J measurable. So I have a sub-sigma algebra of A. I have one random variable that is independent, the other one that is J measurable, and I say the following. For all phi from R squared into R such that phi of x1 belongs to L1 of omega AP, then it is possible to compute the conditional expectation of x, y given J. So what I know that it is something that is J measurable from the definition, but I can be a little bit more precise. The conditional expectation of x, y given J is equal to psi of y, where psi of small y is given by the expectation of phi x. So once again, in this case, okay, where I have what? Independent measurability, then if I want to compute this conditional expectation, in fact, it's not more complicated than to compute an expectation with respect to x. Okay? This is the intuitive meaning of this. So before to do the proof, some comment concerning this. The first comment is that we have already seen special case of this proposition. We have already seen special case of this proposition. what happens if I take for phi of x, y, I take simply, let's say x. Why not? Okay? I suppose that x is near 1. So what is the meaning of my proposition in this case? That the conditional expectation of x given j is equal to what? So this mapping of y, but where the mapping is just the expectation of x, in fact. So in the case where I take phi of xy equal to small x, I just recover the property of the conditional expectation with respect to independence. The fact that the conditional expectation is equal to the expectation in the case of independence. Okay? So taking a particular form for phi here, I recover the property concerning independence. Second remark. If I take phi of xy equal to y, what I obtain? I obtain that the conditional expectation of y given j is equal to what? Y. That is, if I take phi of xy equal to y, I recover the property that when y is j measurable, the conditional expectation of y given j is equal to y. If I am j measurable, my conditional expectation is myself, because I am j measurable. Okay, so it is here two subcases of the preceding proposition. Okay, two statements included in the previous proposition. So the two first remark. Third remark. I will write an equality and you are going to tell me if it is okay or not for you. Are you okay with this equality here? What you did? You said yes. I don't know if I missed something, but I just said, is this one in this way okay or not? You say yes, you say no. If you know the Beatles, it's a song like the Beatles. You say yes, I say no. So yes, no, maybe. Who think that it is yes? Two. Who think that it is no? A bit more. Okay. So the majority is okay in this situation. So now, okay. Why? Why it's not the case? So what I have done here. Okay, I have phi of small y that is equal to this one. I plug inside capital Y, and I have this. It seems to be not that bad, but it's not okay. Why? What is this? This is a number that is in fact an integral. Okay? It's an integral that I can write, for example, I can write it this way. The integral of phi of x w y w dp w omega. Okay? So you have a number in fact, here. Okay? You have here a number. Okay? What is psi of y? Psi of y is also a number, but depending on y. Okay? So, psi of y is equal to what? So, it's the expectation of phi of x, y that I can write as the integral with respect to omega of phi of x w small y dp of w. Okay. If I plug inside capital Y here, if I plug inside capital Y, I plug here something that is a random variable. Okay? Write it this way. But if I can be more precise, I can say that in fact here I have a random variable that depends on an argument inside. I won't call it W because W is used for the integration, but I can call it W prime here, for example, and I have here Y of W prime. So it means that here you have one variable of integration and the other one that is related to this random variable. Here I have a number, here I have a random variable, here this expression and this one, inside you have the same variable and you integrate with respect to this variable. Here you have two different variables and you integrate with respect only to the one related to x. Okay? So this equality is not okay. One is a number, one is a random variable that is a priori not constant. Okay? And typically, the way to see it is this one. Another way, if you want to be a little bit more complete, you can write it this way. It's the integral with respect to r squared of phi of xy dp of xy, the distribution of the pair, and here you have just the integral over r phi of xy dpx, for example. Okay? And you see that when you plug capital Y here, you have the integration with respect to x and not with respect to the capital Y. Okay? You see that it's totally. So to compute this, first you compute this function, that is a function depending on small y, and then you plug inside capital Y. Then you plug inside capital Y, so I don't have this. It's important to have this in. Okay? Are you okay with this remark? It's important to have this in mind. Here I have a number, and here a real random variable that is a priori not constant. So if you are okay, I will erase the three remarks here because I need more place for another one. May I erase the remarks? It's okay? So keep this in mind, because every year, in every final exam, I see this. Okay? So typically, in general, it is an exercise about finance, okay? But in the computation, some mistake dealing with this point. The points in the chapter 0. So I continue my remark, okay, it's the fourth point. It's a reminder concerning Fubini theorem. Okay? So reminder. Reminder on Fubini theorem. So in general, okay, when we have Fubini theorem in mind, we keep in mind that, okay, when I have a double integral, I can do what I want. It's not that bad to have this in mind, but in fact, the Fubini theorem is a little bit more precise. A little bit more precise and typically more precise concerning the regularity of this kind of things. So what is the meaning of the Fubini theorem? So I start from a random variable defined on the product of spaces omega 1 times omega 2 with values in R. Two variables, W1, W2. Okay? Okay. So I have one universe and another one, and I consider the product of these two sets. Okay, so it's the set of the pair. First component in omega 1, second component in omega 2. Okay, so I consider omega 1 as the universe of this probability space. Omega 1, A1, P1. I consider also omega 2, A2, P2. Meaning that I have my two universes, okay, each of them being equipped of a sigma algebra with a probability P1 for A1 and P2 for A2. So do you remind how to build naturally a probability space that is related to this product of universe? So I have omega 1, omega 2. I define a universe that is omega 1 times omega 2. And I say that there is a natural choice for a sigma algebra here and a probability here. Do you remind? No? Yes? What? We define here the product of the sigma algebra, and here the product of the probability. Let me remind what are they? In fact, I have two sigma algebra. So I have sets here that are subset of omega, and here I have subset of omega 2. A natural idea is to say that if I want to equip naturally omega 1 times omega 2 of a sigma algebra, I can see what happens if I do the product of the elements that are here by the elements that are here. Why not? Let's write them this way. A1 times A2 such that A1 belongs to A1, A2 belongs to A2. It's what we call, okay, a rectangle, okay, having for first coordinate an element of A1, second coordinate element of A2. But unfortunately, this one is not a sigma algebra. Very easy to prove that sigma additivity is not fulfilled in this case here. But the idea is not that bad. So what I do in order to obtain a sigma algebra, I consider this. I remind you that this notation is for the smallest sigma algebra that contain these sets. So what we consider as the product of the sigma algebra is the smallest sigma algebra that contain the product of the elements of this type. Okay? It's what we define as the product between two sigma algebras. And this is a new sigma algebra on with this one as a universe. P1 times P2 is a new probability having omega 1 times omega 2 as a universe that is defined on this new sigma algebra. A1 times A2. And how it is defined? It is defined in the following very natural way. For these elements here, we have a very nice formula in the sense that P1 times P2 of A1 times A2 is equal to by what we may expect doing the job component by component. In fact, P1 of A1, P2 of A2, A1 belonging to calligraphy 1, A2 belonging to calligraphy 2. So it's the way we define the product of two sigma algebra and the product of two distribution, two probability, or the product of two measures. The way we do it. Okay? So what is the meaning of Fubini theorem? Fubini theorem, yeah.
Les éléments dans 1 fois 2, forcément cette forme-là.
No. I say the following. It's once again a consequence of the monotone class theorem. I repeat for everybody. I have a new universe. I have a sigma algebra here, a sigma algebra here. A natural way to have a sigma algebra on the product will be to say, okay, I consider this kind of products with A1 as an element of A1, A2 as an element of A2, and try to see if it works. Unfortunately, it's a good idea, but that doesn't work. What I have inside here is not a sigma algebra. But, since it's not that bad idea, I consider sigma of this set, of subset, that is just the smallest sigma algebra containing all these sets. And in fact, in some sense, this sigma algebra is generated by these rectangles here. And I said that what we call the product of two probabilities is a probability, is something that is defined on the product of the sigma algebras. And in fact, if you remind some result about probability theory, if I define something on this one, it is sufficient to define it on these sets, because this one is the smallest sigma algebra containing this. Having properties on this one is sufficient to have properties for everybody. So I just say here that this probability is characterized by the fact that for this very particular case of elements, the probability of a product is equal to this nice formula. It's what we call the product of probabilities. Okay? And you have necessarily seen this if you have spoken about Fubini theorem. Why? Because Fubini theorem tells me the following. If Z belongs to L1 of omega times omega 2 equipped with A1 times A2, P1 times P2. I am L1 in both variables, okay, with these sigma algebras and probabilities. So if Z belongs to this one, okay, I have two things. First, I have the fact that, so if I consider these partial mappings, so if I consider these partial mappings, so what is the meaning of these partial mappings? It just means that what happens if I integrate with respect to the second variable only? This one is just integral z w1 w2 dp2 w2. integrate in omega 2. This one is integral omega 1, z w1 w2, d1 w1. The Fubini theorem tells me that these two mappings here I have two random variables. Here I have something that depends on two variables, and that is a random variable with respect to this choice of sigma algebra. The partial mappings defined in this way are, this one is A1 measurable, this one is A2 measurable. Okay? So, it is the statement you forget in general in the Fubini theorem because you don't like it, the way to express. But what you keep in mind is that if you compute the expectation of z, that is just what the double integral if you compute this one, you can compute it in the order you want. Okay, so you can first, I will write it this way, first compute the integral with respect to omega 1, and then the integral with respect to omega 2, or first the integral with respect to omega 2, and then the integral with respect to omega 1. And in general, you keep only in mind this one. That is, when I have a double integral, that is an integral defined on a product, I can compute them, computing two integrals of lower dimension. Typically, for Riemann integral, if I have the integral with respect to dx, dy, I will have something, first dx, then dy, or first dy, then dx. Okay? But that is, what is important in Fubini theorem is that if you are in L1, the partial mappings defined this way are measurable. And typically, when you do partial integrals here, what you obtain if you integrate this one first with respect to W1, but you will obtain exactly this one or this one. And it will be for you possible to take the integral of the other mapping that is also measurable. Why I do this reminder here? Because typically here, okay, I am in this situation. If I take for what? So what I have here, what is my situation here? So my z is defined which way here? To be coherent with what I have written here. This one. I can define it this way. So, if I take phi, that is from r squared to r, okay, that associate to x, y, phi of xy. If I take for, so I have r times r, my omega 1 is r, my omega 2 is r, I will take for a1, okay, I will take sigma of x, I will take for a2 sigma of y, and I will take for p1 p of x1 and for p2 p of x2. Okay, so if I apply my Fubini theorem in this situation here, from this statement here, I obtain that this partial mapping, that is what happened when I compute the expectation only with respect to capital X, is a mapping that is Borelian, that is measurable with respect to the Borel sigma algebra. Implying that here I have something that is a Borel mapping of capital Y, so something that is J measurable. Okay? So to say what? That when I consider a partial integrals, okay, we always include only these results in the second statement of the Fubini theorem, saying that I can compute the integral in the order I want. Don't forget that if you want to compute the integral in the order you want, the partial integral has to be still random variable to be integrated. Right? The first statement we always forget concerning the Fubini theorem. So I just say that when I am in this situation here, what I have here, from the definition of psi, okay, that this one is measurable, in fact, from Fubini. So I will do the proof next week of this one. Okay, I will finish quickly the chapter concerning conditional expectation. And I will start the chapter concerning stochastic processes. So try to be okay with the notion of measurability, because dealing with stochastic processes, okay, is just to extend what you know about measurability, but in the case where you don't have a single random variable, but a family of random variables. Okay? See you.